Today I would like to discuss with you one of my works that I'm currently doing. That is damage prediction on stiffened structure by using peridynamics. And here is the outline of my talk. First, we will see what is the motivation. Second, I would like to introduce quickly peridynamic theories and why it is suitable for fracture problems. So next, I would like to introduce peridynamics formulations for beam and shell structures. And after that, we will see some numerical examples. And finally is our conclusions. According to the review in 2019, over the past 10 years, we have totally 1036 lost cases for the vessel over 100 GT. Well, that number is reduced from 132 in 2009 to 46 in 2018. Well, it means that our ship structures become more safety. Regarding the reasons for ship loss, we can observe that the main reasons come from machinery damage. However, the grounding or hung damage, which are related to the structure damage, are also very important. Okay, now we come back with this number. If I divide this number to 10, which means for 10 years, and 52, which means 1 year we have roughly 52 weeks, I got 2 cases per week, which means every 3 days or 4 days, we will receive an email to inform us that there are new case of ship loss or a new case of ship damage. Well, it's very big, right? So whenever there are damage on ship structure or offshore structure, we often put some basic but very critical questions. That is, why did the fracture occur? When and where did the crash start? And how it propagated? And our ambition is also the same things. We want to answer all of these questions. We want to understand clearly the behavior of the structure during the damage process. If we can do that, the next step, we can propose some solution to prevent or minimize the potential of damage to avoid some catastrophic failures. So in next part is a peridynamics theory. Before going to what is a peridynamics, I would like to quickly going back the classical continuum mechanics. The equation of motion for a particle in the classical continuum mechanics usually expressed in the partial differential equation. And we know that the partial derivative requires the model have to be continuous. So, and in other words, it will become invalid in the presence of discontinuity. So, imagine that if we are trying to simulate the fracture problems, which means we want to allow the discontinuity happen in the model. So that is some kind of conflict with that condition of partial derivative. As a result, the classical continuum mechanics face difficulties in terms of predicting fracture problem, especially multiply crack paths or crack branchings. In peridynamics, by looking at that difficulties, we express the equation of motion in other form, that is the integral differential equation. And as you know that the integral doesn't require your model have to be continuous or discontinuous or not. In other words, it valid in both cases, and it can be very easily expressed in the explicit form like this. and as a result, it is suitable for damage predictions. I just give you an example in here. Here is a very complex fracture problem of a thin brittle subjected to impact loading captured by Peridynamics. Here is a PD simulation, well-known cutoff experiment, and here is a PD simulation of 3-point bending test. Peridynamics can apply in many applications, for example, to predict damage in composite materials, to predict damage in polycrystal materials, in nuclear materials, or even to simulate the eye structure interaction, including damage. Of course, there are many more applications in Peridynamics, but I cannot show all of this in here. The next part is Peridynamics for beam and shell structures. We know that our ship and offshore structures have typical properties, that is, they are either thin groove structure or very slender. So as a result, if we want to use 3D fashion, which is 3D solid element, to investigate the behaviors of these structures, we will face very big problems in terms of computational cost. Therefore, we need structure idealizations. In fact, in classical container mechanics, we already have beam and shell theories. In finite elements, we have beam and shell elements. So, in Peridynamics, we also agree that we need to have a beam or shell formulation in Peridynamics. At the time we start our project, because the PD theory is quite new, it just developed from 2000. So there were not available a complete PD model for 3D beam or shell structures, for example, like a jacket platform or a ship. So we have to develop by ourselves. To do that, first we develop a PD model for a straight beam with 6-degree freedoms, and then we extend that model for curved beam, and finally we further extend that model for complex beam structures such as a jacket platform. For shell structure, we also start with a flat shell with 6-degree freedoms, and after that we further extend the model for curved shell and complex shell structures. And this part I would like to show some numerical example. The first example here is a static behavior of a jacket platform subjected to static loading conditions. The platform, it consists of 28 beams and is fixed at the bottom and is subjected to transfer force at the y directions on top. The structure dimensions and material properties are shown here. So in order to validate our PD result, we need to compare with a well-known finite element analysis. So we conduct the same example in finite element and we compare one by one for all 6-degree freedoms. So on the left here is a PD result, and on the right hand here is the finite element result. As you can see, the PD result and finite element results match very well for all degree of freedom, which shows the accuracy of the PD model. In this example, we investigate the same jacket platform, but we assume that the platform have initial damage at this location. Furthermore, we also assume sea working conditions including wave, wind and current. And we also introduce a heavy box which can represent the superstructure on top of the jacket platform. The structure dimensions and method properties are shown here. So in order to simulate the behavior of the jacket platform, we need to firstly calculate the loading condition, wind, wave and current load acting on the jacket platform. So we validate that calculation with a well-known software called Sisam Zini, and the results match very well. So after verifying the loading calculation, we apply that loading in the peridynamic models, and we simulate the crack the damage evolution on the jacket platform. As you can see, because we choose very critical wave conditions, so when the wave passing the jacket is completely damaged. An interesting things we observe from this example is the damage occur at the joint locations of the beams. That joint locations are often the very critical location in practice where the stress concentration can be occur. So from this example, we can conclude that in order to strengthen the jacket platform, we need to strengthen the joint location. In this example, a stiffened structure subjected to a constant pressure, we investigate a panel like this. The panel includes a curved shell and 4 stringers. The dimension and method properties are shown here, and the curved shell is subjected to a constant pressure. Similar to the previous example, we first need to validate our PD model. So we compare PD result with finite element result. Showing in the left hand here is a PD result, and the right hand here is a finite element results for all degree freedoms. As you can see, all the result match very well, which shows the accuracy of the PD model. After verify the PD model, next we will conduct some crack problems. In this example, we want to conduct a parametric study on the initial cracks, the effect of the initial crack orientations on the crack propagation. And the plate is fixed on the left end and is subject to incremental transfer displacement on the right end. The vertical displacement. And the crack orientation is represented by angle beta, which is 0, 45 and 90 degree. And when we try to apply the load on the right end, as you can see, for the case of beta equal to 90, the crack propagate with nearly the same direction with the initial crack. On this case, beta equal to 45, the crack propagate only from the tip near the right edge of the plate where the loading is applied. At this tip, the crack is nearly stopped. In the case of beta equal to 0, the crack is nearly stopped at this tip. After several loading steps, finally the crack propagates parallel to the right edge of the plate where the loading condition is applied. So from this example, we can observe that for specific these loading bending conditions, the initial crack angle is not really affect the crack path of the new crack propagation. In fact, the crack propagation, the crack path tend to parallel with the right edge of the plate where the bending condition is applied. In the next example, Another parametric study on a plate with pre-existing crack are simulated, but in this case we are trying to propose a simple solution to prevent or minimize the crack growth. We conduct 3 cases. The first case is the plate with pre-existing crack subjected to bending. The second and the third case, we put 2 patches at 2 crack tips, and we win the case 2 with bigger patches and case 3 smaller patches. We want to see is this solution is really work or not. So as you can see, when we continuously applying the load, in case 1, similar to the previous example, the crack propagate parallel with the right edge of the plate. In case 2 and case 3, we can see that by putting the patches at the crack tip, we can prevent the crack propagation from the initial crack. However, there were new damage positions occurring in both 2 cases. The new position of damage are surrounding the patch that we put on the plate. The reason is, when we put the patch on the plate becomes thicker, and at the transition location between thick part and thin part, the damage occurs. And we capture the same behavior in case 2 and case 3. However, another interesting things we observe from this figure, that is a loading history in 3 cases. In this figure, blue line represent for case 1 and case 2, and red line is case 2 and black one is a case 3. In this curve, the peak values of bending moment represent the highest strength of the plate. Exceeding this value, the damage will quickly propagate and the strength of the plate is quickly reduced. For the case 1, you can see that the maximum bending strength of the plate is around 1400. Exceeding that value, the crack propagate and the strength is reduced. In case 2 and case 3, we can observe that by putting the patches on the crack tip, the strength of the plate is much increased, up to around 2100 or 1900 Newton meters for bending moment. And again, if we exceed that value, the crack propagate and the bending strength is reduced. However, we can also observe that, assume that we have a real plate operating in a real condition, and let's say if the load bending moment acting on the right end of the plate is surrounding the value of 1600. Let's see what happens. By looking at that curve, we can conclude that if we do nothing with the plate will be damaged completely, because the peak values of this curve is smaller than 1600. However, by putting 2 patches at the crack tip, we increase the bending moment for the plate over that up to these values. Therefore, and this value is much bigger than 1600. So, which means that we can save the plate, or in other words, the solution of putting the patches at the crack tip work. In this example, we investigate a box girder subjected to bending. the configuration and geometrical properties and material properties of the girder are shown here. The bending as a loading condition and boundary condition is shown here. So we want to investigate where is the damage location, where it initiates, and how it propagates. And finally, we also want to investigate the residual strength of the box girders. As you can see from this figure, after 40 load steps, the crack initiates at the two corners of the cradle, but that two corners near the right end of the girders where the loading is applied. After 500 load steps, the damage propagates horizontally from two corners to sides of the girders. After 1000 load steps, the crack continue propagating, and it go beyond from the bottom vertically to the sides of the girders. And after that, here is a final damage of the structures. As you can see that from this figure of loading history applied on the structure, when we apply the bending moment exceeding that peak value, the crack start initiate, and then the damage start propagating, and the required applied bending moment is much reduced, and the final value of the bending moment is very small compared to the maximum value, because that is correspond to the final damage of the girders. So in our conclusions, first, in this study, the PD models for beam and shell structures with 6-degree freedoms are introduced. The second, a simple method to prevent the crack growth in a plate with pre-existing crack by putting circular patches at the crack tips is proposed. However, for further investigation, other possible methods can also be investigated by using the same PD models. And finally, details of damage evolution, including location of damage, crack path, crack opening, and residual strength of a box girders are investigated by using the PD shell model. Therefore, further application of this PD model for damage predictions on practical ships and offshore structure can be investigated. Hopefully, unforeseen accident and catastrophic failures on the structures can be avoided. Thank you very much for your attention.